Alrighty. Hi, everyone. We're so excited for you to join us for this session. Not only are you in this room attending the session, there's also a digital audience watching with us online at build.microsoft.com. During the session, you can ask questions through the online chat feature. How can you do that, you may ask? You can scan on the left or right sides of the room. There is a QR code for Pubble, and we have experts located down there that will be answering your questions live. You can also send comments as well. Both our in-room attendees and digital attendees will be sending their questions through the same chat, so you can see what folks are asking online as well. We're so excited to be blending our in-person and digital audiences together in this way. And if you still have any questions after the session, the best place to connect with experts is in the hub on level 5. We'll have plenty of experts there, once again, on level 5. The session will begin very shortly. Thank you so much for attending.
All right, hello and welcome everyone. Thank you so much for joining our breakout session on day 2 of Build. I'm Adele Parsons.
And I'm Jacques van Rhyn.
And today we're excited to talk with you about how to bring AI experiences to all of your Windows devices with DirectML. We will showcase how DirectML scales popular machine learning or ML models across Windows hardware and hardware accelerators, demonstrate how you can leverage popular ML frameworks, and show you how DirectML helps you integrate AI into your native Windows apps and now through the web as well. As Satya and Pavan mentioned in the keynote yesterday, DirectML, a key component of the Copilot Runtime, makes it easy for you to leverage the power and diversity of the Windows hardware ecosystem to scale AI and reach the breadth of your customers. DirectML is a performant, native C++ DirectX API for hardware-accelerated machine learning. It is available as a downloadable NuGet or PyPy package, or also part of the Windows 10 SDK or newer. DirectML follows Microsoft's comprehensive approach to secure software development through its Security Development Lifecycle, or SDL. Because it's part of the DirectX stack, it's built on the solid DirectX foundation, leveraging security features built into the drivers, such as process isolation, memory management, and more. It works seamlessly with Direct3D12 with low overhead and conforms across hardware. This makes DirectML ideal for when both performance is desired and reliability and predictability of results across hardware is critical. Now, I'll hand it over to Jacques to talk high level about how DirectML works.
Thanks, Adele. DirectML clients build a hardware-agnostic description of a network, which is called a DML graph. This graph description comprises both math operators and tensor data, such as shape, data type, and data memory layout that will later be bound to the network. Before a DirectML graph can be executed, it is processed by DirectML's graph optimizer, which performs a series of hardware-aware optimization passes. This optimizes the graph for efficient execution on the target device. Optimizations are orchestrated by the DirectML runtime through queries to DirectX user mode drivers, or UMDs. These UMDs all implement the DirectML device driver interface, or DDI. The DDI is carefully designed to enable specialization to unique hardware features and requirements, while also retaining a consistent experience for users across hardware. This avoids the need for time-consuming, ahead-of-time compilation tailored to every possible device that you may wish to target to reach the extent of your customers. The result of DirectML's graph optimization is an execution plan, which represents the optimized sequence of commands that perform the work described by the original graph. Execution plans are a mixture of DirectML-provided shader bytecode, or DXL, and hardware-specific operations, or native kernels. Clients can record the execution plan into a standard D3D12 command list and may bind different tensor resources, including constant data like weights, to the same compiled graph without needing to recompile from scratch. Once hardware-specific commands are generated and ready to be executed, they're sent to the WDDM or MCDM scheduler to be scheduled on the GPU or NPU, respectively. The Windows Display Driver Model, or WDDM, targets GPUs. The Microsoft Compute Driver Model, or MCDM, is an extension of WDDM and targets non-GPU compute devices, such as the NPU. This enables Windows NPUs to benefit from the same memory management and scheduling infrastructure that GPUs do today. Once the scheduler receives commands from the application, they're scheduled on the target device, based on the priority of the work and other activities happening on the device from across the system. The GPU, for example, might be simultaneously used by various rendering tasks or running other AI workloads. WDDM and MCDM ensure that these tasks are securely isolated from one another and get their fair share of the GPU or NPU, ensuring their reliable and timely completion. Now think about how many Windows devices are out there in the wild and the sheer combinatoric explosion of all the different hardware permutations that they support. DirectML handles all those details so that you don't need to figure this out to reach the breadth of your customers across Windows. Windows truly empowers AI innovation through a diverse hardware ecosystem and enables a range of options for you to leverage when integrating and optimizing AI experiences. We recognize that this brings unique challenges for you to support and scale your AI innovation across Windows to reach your customers. With DirectML, we simplify the options by providing a single hardware abstraction API that you can target for optimization and deployment that scales across Windows. So what does it mean when we say scales across Windows? DirectML focuses on abstracting out the hardware-specific details each hardware option requires to bring a unified API that runs efficiently across architectures. This removes the need for you to understand the hardware-specific details of each machine your customers have. We work closely with our hardware vendor partners to ensure that DirectML performs well and as expected on their respective hardware. Much of what we'll showcase today was made possible thanks to our close partnership with our hardware vendors. There are so many use cases out there. What kinds of experiences does DirectML support today? We recognize that generative AI, or Gen AI, is at the forefront right now, and so we've invested a lot in lighting up these experiences. DirectML lets you leverage these cutting-edge models in your applications with ease. So let's see some of this in action. Here we have several key models like Stable Diffusion Turbo, Llama 2, and soon Mistral, all running locally on Intel's Arc A770 GPU. Pretty cool. Since DirectML runs across hardware, we can take this same code and models and run it on another hardware vendor, such as on AMD's Radeon RX 7900 XTX. And of course, it runs on NVIDIA too, with 0 modifications. Here we have it running on an NVIDIA GeForce RTX 4090. All this with the same code and model. DirectML aims to enable you to focus on building your AI experiences and less on the complexity to scale. Just leverage DirectML to optimize, integrate, and deploy across the Windows ecosystem with ease. Now, some of you might be asking, what's the catch? Do I have to give up performance because hardware functionality is getting abstracted away? Absolutely not. Together with our hardware vendor partners, we focus on tuning performance for many relevant use cases. And this means that you don't have to sacrifice performance for scale. Now, while some of you might have the same type of high-end GPUs that I just showcased, we understand that not everyone who uses Windows has a liquid-cooled, neon-lit gaming battle rig like mine. We want you to be able to build AI experiences that run well both on gaming-style desktops and on the machines that many people use day to day, like this laptop my mom in Cape Town uses to run her business. So what's the challenge with running these key use cases like these Gen AI models on the average day-to-day hardware? The main problem is memory bandwidth, especially when we're talking about language models. Microsoft Research recently released a suite of models called 𝗫3 that aim to tackle some of these challenges to bring language models to local devices. These small yet mighty models outperform models 10 times their size. They really punch above their weight. This over here shows the model card for 𝗫3 Mini. By itself, 𝗫3 Mini is powerful enough or small enough to run on many Windows devices, but why stop there? There's been a lot of research into reducing the precision and therefore size of model weights, a process called quantization. We have invested in 4-bit quantization to support this reduction in size to enable more models across Windows hardware. We're talking about a dramatic impact on the size of the model. 𝗫3's Mini's weights are an FP16, and this means that if we quantize the model's weights down to N4, we're talking about a 4x size reduction. But we should mention that typically the price you pay for quantization is a reduction in model accuracy. And so, if we can make models like 𝗫3 even smaller without greatly impacting accuracy, we would dramatically expand the model's reach on Windows. Our goal is to ensure scalability while also maintaining model accuracy. And so we integrated a technique called Activation-Aware Quantization, or AWQ, that lets us reap the memory savings from quantization while only paying a minimal impact. AWQ achieves this by identifying the top 1% of salient weights that are needed for maintaining model accuracy, and then quantizes the remaining 99% of weights. This leads to much less accuracy loss with AWQ, and as you can see, it provides a concise, accurate answer to one of life's big questions. Perplexity is a measure used to quantify how well a model predicts a sample. Our perplexity measurements have shown that there's only a small loss in accuracy with AWQ compared to the base model. For more details on this, check out our blog coming out later this week. Quantization with DirectML helps you scale further on Windows. Now, let's see the impact of AWQ with DirectML on 𝗫3 Mini. DirectML supports this technique across hardware, which means that 𝗫3 Mini can run across different discrete GPUs. Here we see it running on newer generations of Intel, AMD, and NVIDIA hardware. It will also run efficiently across many older generations of discrete hardware, such as these AMD 580 and NVIDIA 1050 GPUs. It'll even run on integrated GPUs, like this Intel Arc iGPU, that are in your everyday machines. We expect that small language models like 𝗫3 will be incredibly useful for less complicated tasks that benefit from running on local devices. For example, you might use 𝗫3 to distill the key ideas from a lengthy document, to do content creation from marketing teams, to operate a customer support chatbot, as you can see here, or to edit content, such as this talk track today. Now, deploying these models across hardware is simplified even further thanks to the new Generate API built by the ONNX Runtime. The Generate API is a library that wraps several aspects of generative AI inferencing to make it easy for you to drag and drop language models into your apps. This library supports several languages such as Python, C, and C#, and is integrated with DirectML to ensure scale across Windows. For more on this, check out aka.ms/ORT-GenAPI, or the recording for the Create Generative AI Experiences Using 𝗫 session, since it occurred already. Everything shown so far is running across the various Windows GPU generations and hardware offerings. As you saw in Pavan's keynote, and we'll see more in a bit, DirectML is expanding local accelerator coverage to include NPUs, including the new Copilot+ PCs. We're planning also to expand to include dedicated CPU support. With all this expanded local accelerator support, DirectML will fully provide scale across hardware and local accelerator options available on Windows devices. To learn more about how to try this for yourself, check out these various sites. You can talk to our experts at the Expert Meetup or try them hands-on in our lab. Test drive AI on Windows with DirectML, ONNX Runtime, and Olive. To see 𝗲𝗏𝗀𝗀𝗀 with AWQ running on various laptops, check out our demo session tomorrow. Run your AI apps across Windows devices. So far, we have discussed and demonstrated how DirectML scales key use cases across hardware and local device accelerators. Now, let's delve into the ML frameworks that DirectML supports. All the examples showcased so far are running with the ONNX Runtime, or ORT. It is an open source, highly performant, cross-platform machine learning acceleration framework. ORT has a flexible execution provider, or EP framework, to support integration with hardware acceleration APIs such as DirectML. It supports a myriad of languages such as Python, C#, and C++, allowing you to code in your language of choice. It's used for applications such as GenAI, image synthesis, text generation, and more. When you combine ONNX Runtime with DirectML, you really bring performance and scales for your AI experiences to reach your customers across Windows. While we recognize that ONNX Runtime really is best in class on Windows, there are other ML frameworks out there that developers are using. DirectML aims to enable you to leverage popular ML frameworks, and today we're excited to announce that we have extended our PyTorch with DirectML support to a wider range of models for inferencing across Windows GPUs. We understand PyTorch is widely used in experimentation and testing, and realized that it would be great to enable you to leverage PyTorch to test and scale across Windows. Now, with DirectML, you can. PyTorch is an open source, optimized tensor library based on the Torch library. It's used for applications like computer vision, natural language processing, and more. It's primarily developed by Meta's Artificial Intelligence Research Group and provides a flexible interface for building and deploying machine learning models. PyTorch with DirectML is available on the latest versions of Windows and has been updated to PyTorch version 2.2.0 and DirectML 1.13. It's available today as a downloadable PyPy package. PyTorch with DirectML now supports several key GenAI models, including 𝗲𝗏𝗀𝗀𝗀, llama 3, and more. Let's give it a spin. The same types of models shown running with ORT now also run with PyTorch. Combined with DirectML, you get the same hardware portability using the same code and models to scale across Windows. You just saw 𝗲2, llama 2, and now Mistral running on Intel's Arc A770. We can take these same 3 models and code and run them on AMD's discrete GPUs, like their 7900, and on NVIDIA's 4090, all running across the different hardware with the same code and model optimized for DirectML. Let's walk through our 𝗲𝗏𝗀𝗀𝗀 sample to show how to get started using PyTorch with DirectML. You can run this sample in your existing Python environment after installing the latest Torch DirectML build using pip install or downloading from PyPy at aka.ms/torchdirectml. Once you've done this, you can run any of the PyTorch samples found at aka.ms/directml samples. First, you'll need to pip install and log into Hugging Face through the CLI. This is setting up the environment to grab the model from Hugging Face. Second, you'll need to download the model locally from Hugging Face to run the sample. Last, run the model for inferencing, which is feeding the model with data and retrieving its output result. And that's it. To learn more about how to try this for yourself, or try a few others, visit these sites or talk to one of our experts at the Experts Meetup right here at Build. Taking the 𝗲3 sample we just walked through, you can see 𝗲𝗏𝗀𝗀𝗀𝗀 in action across newer generations of DGPUs. Oh, sorry about that. I don't know what happened there. You can see 𝗲𝗏𝗀𝗀𝗀𝗀 in action across the newer generations of different discrete GPUs with PyTorch and DirectML. Let's try again. And you can even run the latest Llama 3 model across the latest Windows discrete GPUs, all with the same code and model with PyTorch and DirectML. As you've heard and seen throughout Build so far, Windows AI Studio has now become AI Toolkit for VS Code. This amazing toolkit will enable many key workflows, including cloud-to-edge usage and a playground experience that enables you to download, fine-tune, and run models locally. We're excited to show you a new cool feature that will be part of the experience with the AI Toolkit. This new playground feature will enable you to interact with various PyTorch models locally with ease. First, you pip install the latest Torch DirectML package to configure the environment to leverage DirectML. Next, you'll pip install the AI Toolkit server locally, which provides access, in this case, to PyTorch models that are optimized for DirectML. Once that is complete, you'll start the server with PyTorch with DirectML as the backend. This sets up the environment to allow you to inference across Windows hardware, in this case, GPUs. And since this is powered with DirectML, there's nothing further needed to run across different Windows GPU hardware. Next, you will select Model Playground, which will be available as a Windows Code extension. And Model Playground is intended to provide access to models from where you are to test for your use cases. Then you will select the server that you wish to connect to, here, and then you'll think of a question and start chatting in the text box. It's that simple. This new playground experience that is part of AI Studio will be available next month for you to try out yourself. Let's ask our question. How far is the moon from the Earth? And we'll submit. And the awesome thing about this is all running locally. Let's give it just a second. Wow, very cool. While we have extended our PyTorch with DirectML support for inferencing across Windows GPUs, our investment won't stop there. Stay tuned in the coming months for additional support across key use cases, local accelerators such as NPUs, and more. So let's recap a bit. You've seen the power and simplicity DirectML brings to enable you to light up amazing AI experiences across hardware vendors, local accelerators like the GPU, and integration with powerful and relevant frameworks like the ONNX Runtime and PyTorch, all for native Windows apps. Now, let's learn from Adele how DirectML brings the same ease of AI scale across Windows through the web.
Thanks, Jacques. Such exciting things showcased today for how to simplify and scale your native AI-enhanced applications across hardware, local accelerators, and popular ML frameworks. But what about web applications on Windows? Today, we're really happy to introduce to you the WebNN developer preview. We're going to show you how WebNN works with DirectML and ONNX Runtime Web to enable fast and secure machine learning on the web. WebNN is an emerging web standard that defines a powerful way to inference ML models for web applications. WebNN allows you to access the hardware-accelerated capabilities of local accelerators, such as GPUs or NPUs, to run machine learning models efficiently and securely. This means that web applications can leverage the power of machine learning without requiring the user to install any additional software or plugins. It also means that web applications can run across different platforms and browsers, as well as protect the user's privacy and security by avoiding data transfer to external servers or cloud services. WebNN can enable a variety of use cases, such as generative AI, object recognition, natural language processing, and more. So how does WebNN execute ML models on the device? Well, WebNN is a web API that defines how to interface with different backends that provide the actual implementation of the neural network operations. One of the backends that WebNN can use is DirectML, which provides performant, cross-hardware ML acceleration, as Jacques demonstrated a bit ago. By leveraging DirectML, WebNN can benefit from the hardware scale, performance, and reliability of DirectML. So how can you actually use WebNN to run machine learning models on the web? Well, WebNN exposes the basic building blocks of neural networks, such as tensors, operators, and graphs. WebNN also supports integration with ML frameworks, like ONNX Runtime Web, or ORT-Web for short. ORT-Web is part of the ONNX Runtime project and is a JavaScript library that enables you to run ONNX models in the browser. To make it easier for you to use WebNN, ONNX Runtime Web extended their execution provider framework to include WebNN as an execution provider, or EP, for ORT-Web. So you may be asking, what kinds of AI use cases could leverage WebNN? I'm excited to show you how Microsoft apps like Edge and Clipchamp are building AI experiences with WebNN. First, let's check out what Edge is prototyping with the AI-enhanced Magnify Image feature using WebNN. Edge lets you enlarge any image by right-clicking on it, selecting Magnify Image, or you can hover over and press the Control key twice. You can see the image is magnified, but in this case, it's still a little bit blurry. So I'm going to click on the AI Enhance button, which uses a super resolution model that runs with WebNN, powered by DirectML, to significantly improve the clarity of the image. Now let's take a look at what Clipchamp is doing. As shown in Pavan's keynote yesterday, Clipchamp is prototyping with WebNN, DirectML, and ORT-Web on the Copilot Plus PC, powered by Qualcomm Hexagon NPU. For their Auto Compose feature. Auto Compose uses AI to craft a video that matches your media and style preferences. You can choose from a variety of video styles, and then let Auto Compose do the rest. Using WebNN with DirectML under the hood, Clipchamp will analyze your media files using AI to pick the best highlights, and then arrange these highlights into a polished video with a professional look and feel. Since WebNN leverages DirectML, Clipchamp is also able to scale these same AI-enhanced features across Windows GPUs, all from the web. Now, let's take a look at how Khan Academy is prototyping with WebNN on Intel's AI PC NPUs. I'm excited to show you an exciting demo through a collaboration between our partners at Intel and Khan Academy. Khan Academy is a nonprofit organization that provides free, world-class education for anyone, anywhere. Khanmigo is their friendly and smart AI-powered assistant that helps learners practice their skills by conversing with them on various topics, giving them feedback, and adapting to their interests. What makes Khanmigo really amazing with the prototype we're about to see is the ability to run speech-to-text capabilities powered by WebNN, DirectML, and ONNX Runtime Web. These are cutting-edge technologies that enable fast and accurate speech recognition and natural language processing in the browser. This means that learners can access Khanmigo from any device, anywhere, and enjoy a smooth, seamless conversation with their AI tutor. We're very excited to show you this feature running on Intel's AI PC NPUs, which can deliver high performance and efficiency while consuming very low power and memory, making it ideal for web-based and mobile applications. So, let me show you how Khanmigo works. I'm on the Khan Academy website, where I can find Khanmigo under the Tutor Me section. I can start a conversation with Khanmigo by clicking on the microphone icon and speaking into my laptop's microphone. I'll ask Khanmigo, give me a practice algebra problem. Khanmigo will listen to me, transcribe what I say, and respond with a relevant reply. You can also see the NPU spike in the task manager as the speech-to-text model is executing on the device. Thanks to WebNN, DirectML, ORT-Web, all powered by Intel's AI PC NPUs, it runs very fast and smoothly in the browser, all while executing the model locally on the device. This makes it very accessible and convenient for learners of all ages who can use it anytime, anywhere. We're very happy to showcase this collaboration with Intel and Khan Academy. So now that you've seen some great demos on what WebNN can do, let's walk through the workflow for how to use WebNN with ORT-Web and DirectML. First, you need to import ORT-Web into your web application, either by using a script tag or a model bundler. ORT-Web is available as an NPM package, or you can download it from the GitHub repository. Second, you need to configure the WebNN EP, which is the component that handles the communication between ORT-Web and the WebNN API itself. You can do this by passing an options object to the ORT.InferenceSession constructor, where you can specify things like the device preference, which we have here as GPU, so we're utilizing DirectML's local hardware acceleration, and power preference, which we have here as the default. Third, you need to create a model session and pass the model path, whether that's bundled with your application or called from a platform like Hugging Face, and pass in the session options we defined above. Fourth, you run the model session, which is the process of feeding in that input data and getting the output predictions from the model. You can do this by calling the session.run method and passing in the input tensors, which we have here as the feeds. The session.run method returns the output tensors, which can then be used for your application logic. And that's it. You just learned how to use WebNN with ORT-Web to run machine learning models in the browser while taking advantage of the scale across local hardware with DirectML. WebNN supports key use cases that you can try out today with state-of-the-art models. One of the main goals of WebNN is to enable you to leverage the latest advances in AI on the web without having to worry about the underlying hardware or software platforms. To illustrate this, we'll show you how WebNN can run a powerful Gen AI models on the web and use the same code to run across the breadth of Windows devices, thanks to DirectML. Here you see a website that runs Stable Diffusion Turbo, made possible by our partners at Intel, that you can try out for yourself at aka.ms/WebNN. This website runs Stable Diffusion Turbo locally on Windows GPUs by using WebNN with DirectML and ORT-Web. Right now, this is all running locally on an Intel Arc A770. But with the same code, you can see it run on different machines and hardware vendors, such as the AMD RX 7900 XTX, and now I can switch over to an NVIDIA RTX 4090. As you can see, WebNN combined with DirectML and ORT-Web enables you to write once and run anywhere, while taking advantage of the performance and functionality of the underlying hardware. To learn more about the WebNN developer preview, you can check out these various sites, specifically the aka.ms/WebNN. You can also talk with our experts at the Expert Meetup, or try them yourself in our hands-on lab. Learn how to accelerate Stable Diffusion here at Build. There's one more session tomorrow morning at 8:30. The WebNN developer preview available today has support across Windows GPUs with NPU support coming soon. As you've seen today, WebNN is a web standard that defines a powerful API for running ML inference in the web. It enables applications to leverage the hardware-accelerated capabilities of the device, such as the GPU or NPU, for efficient and performant ML inference. WebNN works with different backends that provide the actual implementation of the neural network operations, such as DirectML on Windows. WebNN also works with various web frameworks and APIs that provide the high-level interface for running machine learning models on the web, such as ONNX Runtime Web for ONNX models. Together, WebNN, DirectML, and ONNX Runtime Web form a powerhouse trio for fast and secure machine learning on the web. We're deeply grateful to our amazing partner, Intel, for their vital contribution to the WebNN API and their support in launching the developer preview today. We really hope you enjoy the WebNN developer preview. As we've demonstrated throughout our session today, DirectML really empowers you to bring your AI innovation and simplifies how you can scale your AI experiences across Windows. DirectML is a single, cross-hardware DirectX API that simplifies AI deployment and optimization across Windows. It supports across hardware options and local accelerators like GPUs and NPUs. DirectML integrates with popular ML frameworks like ONNX Runtime and the newly extended PyTorch support for inferencing. DirectML enables you to light up amazing AI experiences natively and now in the web with the WebNN developer preview, all to enable you to scale AI across Windows and reach the breadth of your customers.
To learn more or to get started today, check out these various sites. You can also talk to our experts at the Experts Meetup right here at Build, or try our hands-on samples in our labs, or visit any of these sessions here at Build. Awesome. We have a few minutes left to answer questions. We'll be right down there. We're eager to hear from you all. Thank you.
Thanks, everyone.